you. So I'm going to talk about the methods behind the first analysis I showed you all yesterday, and I'm going to kind of try and frame that in the context of decisions one has to make when modeling growth. And so these are just some of the decisions that I see that we have to make when we're thinking about how to apply these growth models to larger sets of species. And so the three questions I'm going to talk about are which model to use, at what population scale should we model growth variation, and how do we deal with and account for measurement error and making sure what we're measuring is growth change and not just changes in sampling or measuring. So I think this is the third or fourth time this picture is going to show.
It's a good one.
It's a good one, yeah. This is a Lombard-Lampe growth model, as we all know and love it. It was kind of designed to model the growth of an individual fish based on that differential equation that shows the difference between anabolic and catabolic energy expenditures and how those relate to increases in size and weight. So there's two parameters, actually three parameters, either L0 or T0, sort of tell you where this intercept falls. K, which is the slope at minimum size, and L infinity, which is the mean length at maximum age. So this is the most commonly used growth model to model fish populations by far. And usually it's just kind of used as a constant curve like this. So you have, this is Pacific halibut, and you have age on the x-axis in years, and size on the y-axis, and the curve kind of goes up and asymptotes, or doesn't really asymptote for some species. But when you actually look at what real growth data looks like, you see that putting one curve through this massive cloud of points is probably not going to capture all the variation that you're seeing in the population. And so the first way you could model growth, and what Alan has done, and I think Tim Miller has done, that they're going to talk later, is just fit different curves. So whether you're going to separate it by cohort or by year or by area, you can just fit a unique curve to each segment of the population that you're interested in. There's a lot of pros of this approach. As Tim talked us through, it's based on mechanisms, it's based on really strong theoretical background, and it's easy to translate back to a population model. Most stock assessment models, or many stock assessment models, use this curve implicitly in the model. So when you're trying to take the growth variation you measure and put it back into the population model, it's really clear how you would do that if you're using the Lombard-Lampe. And it's also really easy to link growth variation across ages. So fish are different sizes at different ages, and so if you have the Lombard-Lampe, that already gives you what you assume your structure is between the relationship between size at each age. But there are some issues with it as well. When I started out trying to fit this model to the number of populations I was dealing with. And the first is that, as we've heard a lot, there's inherent negative correlation between those two key parameters of K and L infinity. And so you often need to make a priori restrictions or assumptions about the joint distribution of the K and L infinity parameters to be able to fit these models. You need to say, okay, I'm going to fix K and estimate variation in L infinity, or vice versa. And the same for T0 or L0, which we don't talk about as much. And for me, I was really interested in modeling annual variation in growth that occurred across different ages in the population in the same year. And so it turns out that's really hard to fit a model to, as I found after struggling with it for about 6 months. Because if you are a fish and your growth parameters change every single year, you're basically shooting for a moving target. And so we generally don't have enough data to say, okay, well, if I'm born in year 1987 and I'm going to grow with these parameters at 88, and then these parameters in 89, and these parameters in 90, it becomes a problem where your model is kind of over-parameterized, and you don't have enough data to fit that. So what I ended up doing was using mean length at age data from fisheries and scientific surveys. And so this is the same axes, but instead here you have, this should say years, not age, sorry. So the x, it's not the same axes. The x-axis is still time, but now we're talking about years of the time series. And the y-axis is size. But in this case, each line is its own age. And so this is what some empirical data for mean length at age in the California current looks like from fish, from younger fish all the way up to older fish, where each fish is line. And yeah, ignore the poorly labeled axes. So I decided just to look at mean length at age and not assume a von Bertalanffy growth curve. And so what I did is I calculated the normalized deviations from mean length at age. And so zooming in on some of that time series, I would say, okay, for an age 3 fish, this is its mean length across some reference period of the time series. And then just take the difference between what the mean length was at a given year and the mean length across the reference period. And then those were basically my response variables. I'm showing that in math instead of pictures. That's what these x values are what I'm going to call my anomalies. And so it's just standardized anomalies across so that you have a value for each age at each time that's sort of on a more standardized scale across ages. Okay, and then the second question I mentioned is, at what population scale do we want to model growth variation? And to do that, I'm going to use this cartoon illustration to talk about the different types of variation. And so for illustration purposes, the first is just the null model. There's no growth variability. So on the left-hand side here, you have length at an age against length at the age right after that. And on the y-axis, you have, on the plot over here, you have mean length against time. And so if you have no growth variability, this is just a straight line. And if you were looking at, this is assuming there's no measurement error, which we know there is, so it wouldn't look this flat in the real world, but assuming you have perfect information, you would just see kind of a flat line over time if there was no growth variation in the mean length at age plot. And so the first type of growth variation we wanted to measure was initial size variability. And I think this is what Tara mentioned earlier, the idea that when you're young, you sort of start off at a given age. So if you're age 3 in this time period, you start off kind of small. If you're age 3 in this time period, you start off kind of big. And that initial size that you're at affects how you grow for the rest of your life. However, you'll notice this plot on the left is not affected because we're assuming that the growth rate between this age and this age is the constant across all the different ages. They just started off at a different place. Next, we modeled cohort variability. So here you can see what happens here is that if you were born in 1991, 1992, or 1993, you would have a higher growth rate throughout the course of your life, or a lower growth rate throughout the course of your life, depending on which cohort you belong to. And so this, in contrast to the first example, initial size variability, we would say, okay, all of the fish kind of recruit at the same size, but then some of them, as they get older, either start to have slower growth rates or bigger growth rates, resulting in a depressed or larger than average size at age in the future.
Why did they recruit the same size?
We were just trying to, well, it wasn't technically the same size. We actually used a distribution, so it was random around the mean size. But I only ever looked at one type of growth variation, but other people have used this model to look at multiple types of growth variation in the same species. So you could definitely do that too. I didn't. And then we wanted to model annual variability. And so this is what I mentioned previously. This was what was really tripping us up with the von Bertalanffy model. So in this case, your growth rate is not dependent on the year you were born. It's dependent on the year that it is. And so what you end up seeing in this case on this left-hand plot is you would see across ages, there are certain years where all the fish are smaller, or there are certain years where all the fish are bigger. And so this is affecting across cohorts. And so because the von Bertalanffy is so widely used, we felt we had to justify this new model to model growth variation. And so we did a simulation analysis. We used a von Bertalanffy operating model with specific parameters that corresponded to those types of growth variation to generate some simulated data. And then we fit our statistical model. And then we saw if our model could correctly match the type of growth variation pattern that we put in our von Bertalanffy. And what we saw is that when there actually was growth variation in our operating model, which is here denoted down the rows as the true, we got it right 100% of the time. However, when there was not growth variation in our operating model, we sometimes still detected it. And so just based on the amount of observation error we put in our simulation analysis, there's definitely a tendency here to overfit. And so we took this and kind of kept it in the back of our minds as we move forward in looking into real data. And as you can see, most of the time that lack of variation was mischaracterized as an annual effect and then a cohort growth effect subsequently. Okay, and so you heard a little bit about the application of this yesterday. So just this schematic, we had the data that I talked about, we put it through this state space framework in a Bayesian context, and then we did model selection to choose between the different types of growth variation. And across the, I've already shown you kind of the time series results, so here I'm just gonna talk about which type of growth variation was selected for all of the 3 large marine ecosystems we looked at, and then the total. So the annual growth variation was by far the most common that we saw across ecosystems. And when you looked at the Bering Sea and Aleutian Islands, this was actually the only ecosystem for which the initial size model was selected more often than the annual model. For the California current, the annual model was selected the most, and also for the Gulf of Alaska. And I mentioned this a little bit yesterday, but because of that tendency for this model to overfit, we did remove those species that had that flat line, even if they were suggested by model selection to have an annual or an initial size effect. Yeah?
Do you have a story why the Bering Sea might be different?
It's coming.
Okay.
Yeah. Okay. And then finally, my final third point that I think we have to think about is how we deal with measuring and sampling error. And we talked a lot about this morning, so this might go over some things we've already talked about. So forgive me, this is kind of a cartoony example from my dissertation defense because I didn't want to go find pictures of fish because I've never actually seen a fish other than on a plate. So it was easier for me to do this. No, I went on one field survey ever, but I'm not a field or experimental biologist. I do math. Yeah. So my example is with people, not fish. So I think when we, if we really wanted to measure growth, we would measure growth the way we measure growth of our kids. We would have one kid and we'd have like some lines painted on a wall and we would measure that kid over time. And in fish, this happens if you have repeated sampling through tagging studies. However, we almost never have that, certainly not on the scale of data we're thinking about. What we have is like a sample of fish that are the same age, similar to having like a class of school children. And we have some summary statistics about that, or we maybe have the individual length, but we don't track the same people over time. We just track cohorts over time. So that's one issue, is just the inter-individual variability, which Tom really summed up really well. And finally, I think if we were thinking about how sampling varies over time, we're not even just sampling like a class in Seattle over time. We're sampling across many different regions. And maybe the spatial scale isn't quite as dramatic as in this example, but it's quite possible that if we were to take a sample from North America one year and then South America the next year, we would see some differences in growth that had nothing to do with actual biological growth. It's just because we sampled from a different area. And of course, different data sources vary in quality and bias. So you can have some data sources that are just really imprecise and noisy, or you can have data sources that are systematically biased. So say someone was always rounding up when they measured a fish or a kid in a given year. And we've seen this in some data. There's like some evidence that people like to classify things as ending in a 5 or a 0, right? Rather than a 1 or some messier number. And so to deal with that in this study, talked a lot about state space models, and they sound really fancy, but I think the biggest issue is actually not the model structure so much as the cleaning and corrections you do to the data before it goes into the model. And I did a lot of that. That was probably more of the work that I did processing this than actually like running the model. And there's probably more than just the 6 I've put up here. The first is selectivity. And so we were using commercial data. Hopefully survey data is a little bit more uniform selectivity over time. But we had to figure out how to deal with the fact that we were selecting different, selectivity was changing over time and changing over area. And so to do that, I just only analyzed the fish that were fully or very close to fully selected by the fishery. Which was, there are clearly better ways you can do all of this. I'm just going to talk about what I've done, and we can maybe come up with better ideas. The second is gear. So gear type is going to affect what type of fish you're catching. And so I separated out the gear types, the biggest gear types, into different observation equations, and then I removed any gear types that were not sufficient sample size on their own. Then we have aging error, which I don't think I need to talk about anymore, other than to say that I had a covariate which represented the percentage of fish in each year that were aged using what I classified as less accurate measurement, which was surface aging or scales or something that wasn't sectioning or break and burn. There's the location of sampling, and so I used latitude and longitude as potential covariates because we know even in the survey data in the United States, the location of the survey has changed over time, and so that can definitely impact what you're seeing for growth. Also included season. We had some data from fisheries that operated in the summer and some data from fisheries that operated in the winter. And so each of those was, again, separated out in the observation equation. And finally, depth. This was a proxy both for the sort of on and off shelf gradient that I showed in the Alaskan waters, and also the fact that in the California current, there's been offshore movement of the fishery at a certain point in the time period that can then affect your sampled length at age statistics, and so that was also included as a covariate. Okay, and again, state space models also help you disentangle observation error from process error, and largely this is because in a state space model, you can have multiple sources that inform of observations that inform the same underlying true process, and so we put our covariates that we thought might affect measurement in these observation parts, and then we were able to separate out data by survey and fishery, and potentially by season, and also sometimes by year. So that in general we had kind of 3 to 5 distinct time series that were then informing the same underlying true growth. And so we hope that the model would be able to say, okay, if you see a wiggle here, but not in the other 2, then account that for, say that that's observation error. But if a wiggle is incorporated in all 3 of these time series, it's probably actually real. It's not just a sampling artifact. And so one of the answers to Alan's question, I got review comments that were like, well, what happens if you like remove one of those data sources? And so we did that for the Bering Sea and Aleutian Islands. We took out the survey data, and we saw what happened if you only used commercial data. And what happens is a lot of the estimated growth variation that had said it was initial size switches to being annual. And this is probably because this commercial data has annual sampling changes because it's a fishery that don't happen in the survey. And so I'm not sure. I think there could be a biological reason for the commonality of the initial size in the Bering Sea and Aleutian Islands, or it could just be, to Tara's hypothesis, that this really is the most common source of growth variation we see, but if we don't have the high quality data, it can switch and suggest that there are annual changes when there's actually initial size changes. So a summary, for the way I was looking at annual growth changes, I found it easier to use just a time series model. It was not the von Bertalanffy. We found annual and initial size effects that were most common. However, when we did remove survey data in one example, we saw that the classification switched from annual to initial size. So that's a good reason to be skeptical sometimes of if we don't really have a long time series of good survey data of the results we might be detecting. And so I think implications for our work is at what spatial scale do we want to think about growth variation? And also, if we do decide we want to use a von Bertalanffy, how well can we inform those assumptions about how K and L infinity covary for a given population? I think we should think about which population segments we expect growth to vary over. And also enumerating for each data set the covariates, things that have changed sampling, and then could introduce bias and perhaps some of more of that noise that obfuscates the signal of true growth change. And so I'll just put my collaborators up here and happy to chat more about how we actually analyze growth.
Question, that sort of bar chart where you had the strength of the different sources of variation for the 4 areas. So what was striking about that was how the annual was always bigger than the cohort, but is the cohort effect essentially buried in your initial size effect?
Maybe, yeah.
So is that really the cohort effect in the way you've analyzed your data?
Mm-hmm. I think
if it is, that would make sense because otherwise, in that respect, I don't know what cohort is capturing.
Yeah, it's always kind of hard. I don't think I explain it well.
That's the spatial structure of the data set each year.
It's I don't know about spatial, but it's I think it would be selected if you saw a unique growth variation for each cohort, but then the initial size was on average the same, I would think.
Because there should be a cohort effect in that they're not a uniform size all the time every year. So, but I think that's what I think of initial size as a cohort effect.
I mean, yeah, they definitely both operate at the same scale.
Right.
It's just at what age within that scale they operate.
That would be, I mean, there's a lot of things that would account for cohort-specific variation, one of which is what you're talking about, sort of an initial T0 that's, say, large, and the animals then proceed along that same trajectory as large. And then the other effect would be is if there's so you're going along cohort, and then you have a shock of a year effect. And then if that shock of a year effect is across all animal in that age across the years, then you have a year effect. But I would say it's, typically thought of as a, compensatory process.
Yeah, but to analyze the data at the starting point, you had standardized it, you normalized it, right? So that's why you're taking this approach to isolate out the initial size.
Yeah, and it could just be that the cohort effect you know, if we hypothesized it might happen, but we were wrong and
Yeah,
it didn't
yeah.
really come out, so.
But it's not surprising given how
Yeah.
how you've processed the
Yeah.
response variable.
Yeah, and all of the species that had estimated cohort effects were kind of those flat trajectories, which makes me think maybe it's just capturing variability more so than, whereas the annual and initial size effects were more substantially different than 0.
If you think about the effects of temperature, say, or some other covariate on those patterns, whether it's a cohort effect or an annual effect, it actually could affect both, right? Because if you're a cohort and you're a certain size, and you're in a window where temperature is a critical kind of factor, and you have a high temperature and you're able to maximize growth or something, then you continue on as a relatively large fish.
Yeah, and I should say, I somehow like never even thought of combining effects in this analysis. Like it was just, I just didn't do it for no good reason. But Cecilia O'Leary, who just got her PhD at the University of Stony Brook, she applied this model to summer flounder and found the best model actually included both. So it was both an initial size effect and an annual effect. So I definitely think that that happens, and I just didn't do it for these stocks, but it might be something to think about. Can I ask Daniel?
So when you for the Gulf of Alaska data, when you only looked at the survey data, did it also vary with both, or is that more constant?
I don't think I removed the commercial data from the Gulf of Alaska. I think I only did it for the Bering Sea and Aleutian Islands.
Okay, but let's say, because the results you showed was only for the fisheries, right? In the table.
Oh yeah. Oh, that was for the Bering Sea.
Oh, so okay.
Yeah. Yeah.
Oh no, I mean the end table. The table in the end. Sorry.
Where?
Oh yeah, sure, yeah.
This is it. I was like, I think this is the only
No
table.
data types or commercial only.
Yeah, so it was with survey data, or if you remove the survey data.
And then did you have to remove also the commercial?
No.
Because you hope, of course, that it's more stable.
Well, technically I have in the second analysis that I showed yesterday, the VAST, but that's a different model, so it's kind of hard to compare. Yeah, but I could certainly do it for this too.
So it might be that, I mean, I don't know how this will all play out, but commercial data maybe be an undesirable data source, although it could potentially provide information on time-varying selectivity of the younger fish. But the other way possibly to deal with that would be if you're using just survey data, could you incorporate kind of a random effect in the model that would allow for some random variation in, say, the initial age at selectivity? Because if you start chopping things off like you did sort of at some age group and discarding all that stuff, you might be discarding a very informative portion of the life history of the animal.
Mm-hmm.
The consequence, however, is that you may have to explain some of the variation in that portion of animals in the size at age due to some more random effect like time-varying selectivity.
Mm-hmm.
Which wouldn't necessarily, I mean, wouldn't be a fishery effect, it'd be more of a temporal effect on how the survey interacts with, I suppose, the size of the animal. Any thoughts on that possibility?
So you're thinking more like a delta model where you have a random effect that then, you have a parameter that represents age of selectivity, and then based on that age of selectivity, you analyze growth variation only in that species, or you're thinking age of selectivity would be like a covariate? Random effect.
Well, I don't know. They're typically in a stock assessment model, and most of them that I've seen, I haven't seen all of them, but there's typically a time-varying selectivity, which is a random, random process, and it just basically adjusts how the initial size of the animal enters the available capture, and then how that sort of response variable is measured. So I don't know, it's just an idea, but I'm just trying to think of how we might explain some observed variation in the data that isn't necessarily a process error, but could be a sampling error.
Well, the observation error is a random effect.
Right, I understand that, but it's parameterized in a different way here.
Yeah, I guess I'm having trouble wrapping my head. So you're saying put all the data in, but then just have selectivity be a random effect rather than just remove
Something like that. It's just kind of a way to justify using data that I think might be informative to us, rather than saying, okay, if you cut, say, Pollock off at age 3 or 6, what was that?
I would have to look at it.
Yeah, but what I'm saying is, Pollock has already spawned, which, the age at first spawning is 50% age at spawning is like 3, age 3, right? Cod, it's probably age 4. And so if you truncate at 6 or 7 or something like that, you're already in the adult phase, and that's what you're stuck with.
Yeah, I mean, maybe it's just I need to think through how that practically would work. Right now, I don't understand that. I'm getting put in the model, but I could certainly.
Well, I'd have to
think
see
about
the code and put it in.
that. Yeah. Yeah. Okay.
Just one more comment.
Yeah.
I like the idea of looking at the combined effects, and that if we apply this box that we have here, I think that would be important to do.
Thank you.
I have a question, Christine.
Oh yeah, sorry.
So I'm trying to kind of frantically go back and look at some of the talks I'll be giving later. But when you talked about the model being over parameterized, were you modeling the process errors as kind of fixed effects then, or?
When you mean when I was talking about the annual effects?
Well, yeah,
The
you mentioned
Baumgartner
like
fee?
if K was changing every year, then you say that it's kind of like chasing a moving target, and model is kind of over parameterized for your data set.
Yeah.
Is that, so in the models that you showed where you have a stated model with both process errors and observation errors, so you mentioned observation errors are random effect, are the process errors random effects too, or are those fixed effects?
Yes, they're random effects as well.
Okay.
Yeah.
Because I think some of, like, the model I'll show that Jim and Carolina did, I think they did a fun lengthy model and they had all kinds of random effects going on within the model, I think, or so.
Yeah, and I was trying to do it at the same time and I wasn't sure how they did that because it wasn't working for my data, and it might just be that because I was using so much commercial data, those changes in sampling were obfuscating that changing growth, but yeah, I don't know. I was having trouble getting it. Or, oh no, you know what it was? They were putting the variation in K. And I was trying to put it in L infinity.
Okay.
And I think I think it's easier to fit a time varying K than a time varying L infinity because the K is, just your slope as you're going up. Yep. But if you're shooting to be a big size fish or a smaller, and we could have put variation in K, but Tim was really adamant that because the L infinity incorporated both the anabolic and the catabolic effects, that we should really be focusing on changes in L infinity rather than changes in K.
Okay.
I think that was the difference between mine and Jim's. And then he had it also on condition factor.
Yep.
Yeah, okay.
Jim will let you call, he might call in there.